Okie dokie. So I'm going to start by kind of drawing my picture. So 0, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, negative 5 pi over 2, negative 3 pi, and then negative 7 pi over 2. So we're talking about quadrants 2 and 3. So far, so good? Okay. Then using all silly turtles crawl, I can see that sine is going to be negative in quadrant 3. Good morning. So again, noting that theta is negative, I'm going clockwise. So that's my theta, right? Okay. My alpha is then here. Still doing good? Okay. So I noticed that the last axis that theta crosses is a vertical. And since theta is negative, that means we're going to be adding alpha. Where alpha is sine inverse absolute value negative 0.44. So want to check my mode and make sure I'm in radian mode. We were doing things last time where we're in degree mode, so want to make sure that I've switched back. And I'm not going to type the absolute value into my calculator. I'm just going to do that part in my head. So it just saves me a lot of button pressing. So I get negative 897. So to check that right quick, sine of that answer ought to give me negative 0.44. Which it does, and that value better be between 7 pi over 2, which it is bigger than, but still less than negative 5 pi over 2, which it is smaller than, so I am quite certain that I have the correct answer. Does that feel okay, Mackenzie? Okay? Mackenzie? Sure. Okay, so same idea. This time notice that theta is positive, so I'm going to be going counterclockwise. So let's see, we're 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and then 4 pi. So we're talking about quadrants 3 and 4. So all silly turtles crawl. Cosine is positive in quadrant 4. So there's my theta. So far, so good, Mackenzie? Okay. And then my alpha is here. Since the last axis that theta passed through was vertical and theta is positive, I know I'm going to be subtracting alpha. So 4 pi minus alpha, where our alpha again is cosine inverse absolute value 0.87. And then calculator time. So I get 1205. And just to check that, cosine of 1205 should give me 0.87, which it does. 1205 should be bigger than 3 pi, which it is, but less than 4 pi, which it is. So I think we got the right one. Does that feel okay, Mackenzie? Was the answer key wrong on one of these? You think both of them? Somebody else had asked me, I know about one of these two, and we found that the answer key was wrong. Like, I think it was giving me the negative. This one, I think I was getting negative 0.87 with the answer on the answer key. So, Evan.
So when you subtract the alpha versus add?
So it depends on whether alpha or the theta is positive or negative. So if theta is positive, like this previous one, if the last axis that we pass through is vertical, then we're subtracting alpha. If it was horizontal, we're going to be adding alpha. And if theta is a negative, they just switch.
Yeah.
So vertical is then going to be adding, and horizontal would be subtracting if theta is negative. So just the reverse. Is that okay?
Yeah.
And that's the easiest interpretation from the picture. Like, you can always like reason it out by kind of looking at what's going on also, but like if we can simplify it down to just like what was the last axis I crossed, you know, that's usually a little bit faster for us. Okay. Anyone else?
Yeah, go.
Okay.
Could you do number 7?
From the same sheet?
Yeah.
Sure. So again, we'll start with our picture. So I notice that theta is negative, so we're going to be going clockwise. So 0, and then negative pi over 2, negative pi, and then negative 3 pi over 2. So we're going to be in quadrants 2 or 3. All silly turtles crawl, I'm going to use to figure out when sine is negative. So that would be quadrant 3. So when I draw my theta, again, I'm drawing it clockwise since theta is negative. So there's my theta. So this is my alpha here. Since theta is negative and the last axis that we cross is vertical, we are going to be adding when theta is negative. Again, where alpha is sine inverse of the absolute value 0.56. So negative pi plus sine inverse 0.56. Again, I do the absolute value in my head. So I get negative 254, or I'm sorry, 255. So sine of that needs to give me negative 0.56, which it does. That number needs to be bigger than negative 3 pi over 2, which it definitely is. and it needs to be smaller than negative pi over 2, which it definitely is.
So when you go over and when you add the minus pi for theta, is it because
Where I'm getting the minus pi from?
yeah, it's not
So
like a boundary,
So you're looking at the part that makes up alpha.
right?
You're just using the part of the x-axis that
Oh,
is you're making up your
I
alpha.
see. So if it was the other way around.
So if it was on the other side, you'd had the other side of the x-axis. If alpha's it's just whatever side alpha of the x-axis alpha uses, that's the value you're going to be adding or subtracting alpha from,
I see.
or 2, I should say. Mackenzie? Sure. And I'm going to drop the unit circle in here since the directions are asking me to use the unit circle. Just kind of makes things a little easier if I just have it right here to refer to. Okay. Oops. Okay. So this one's a little different because you're not giving a range of values, but that's okay. What I'm basically going to do is I'm just going to rewrite this as x's and y's using my definition of the unit circle. So I know that the sine is the y coordinate and cosine is the x coordinate. So I'm really just looking for the place where my unit circle point is 1/2 comma negative 3 over 2. So that needs to be in the 4th quadrant, right? Where x is positive but y is negative. So 1/2 negative 3 pi, or root 3 over 2. So it should be 5 pi over 3. That's it. Is that okay? So again, like maybe not totally obvious, but that's by far the easiest way to kind of handle one of those is you just turn them into coordinates and then you're basically done, you know? So the unit circle is cosine theta comma sine theta. So cosines are your x's and sines are your y's. So on number 3, you'd be looking for the y coordinate being negative 1/2 in that range of values from from pi over 2 to 3 pi over 2. Does that feel okay? Peyton. 9, you say? Sure. Okay. We'll start by just kind of drawing the picture to figure out what quadrants we're looking in. So 0, pi over 2, pi, 3 pi over 2. So we're going to be looking in quadrants 2 and 3. All silly turtles crawl. I'm looking for the place where, well, cotangent and tangent are going to be positive and negative in the same locations because they're just reciprocals. So I'm looking for where tangent is positive between those two quadrants. That would have to be quadrant 2. So there's my theta.
Wait, you said there's like why is it there?
I'm sorry, what?
Can you just say what you said?
Well, cotangent and tangent are reciprocals.
Okay.
So where one is negative, the other is negative.
Okay.
So I'm just looking at where tangent is negative
Okay.
between quadrants 2 and 3. Right? Okay. So I remember that cotangent is x over y. if I just like multiply both sides by y, I'm basically looking for the place in quadrant 2 where the x and y coordinates are just opposite. Does that feel okay, Peyton?
Yeah.
So if I go and I look there at my unit circle in quadrant 2, that's the spot where the x and y coordinates are just opposite. One is positive root 2 over 2, the other is negative root 2 over 2. So I'm looking for 3 pi over 4 is my value for theta. Cool? Okay. Yes, Paul.
So like for number 11, could you use the unit circle for number 11?
Yeah. So again, 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. So we're looking here. All silly turtles crawl. So tangent is positive in quadrant 3. So that's my theta. So I'm going to remember that tangent is y over x. Now the problem here is if I go and I look for a place where the y coordinate is root 3, or has a root 3 in it, and the x coordinate has a 3 in it, there's no coordinates anywhere on my unit circle with just a regular 3. So what I'm going to do is I'm going to think about regular 3 as root 3 times root 3 and reduce this. So I'm going to look for the place where the y coordinate has a 1 in it and the x coordinate has a root 3 in it. So if I go to my unit circle and I'm looking for the place where the y coordinate has a 1 in it and the x has a root 3 in it inside of quadrant 3. So that's the value I want, is 7 pi over 6, but that's not actually my answer. Because I notice when I look at my picture, I go around one full time before I go to my terminal side. So I really should be adding 2 pi to this. And when I make my common denominator and do all that jazz, I get 19 pi over 6. Is that okay? So the trick was really having to reduce that root 3 over 3 to get it into a form where it would be easy to pick out what coordinate you were looking for. And had you not seen that trick before, that's a tough one to come up on all on your own.
So it's just like a single number, like for times root 3. Like you just look for the unit circle.
So you're thinking of x over y, so you're looking for root 3 for the x and a y for 1.
Okay.
And again, they just have to be in it because you're dividing, so they could be like fractions that like get canceled out or whatever.
Okay.
So if we know that it's a unit circle value, that makes life a little bit easier. I don't have to worry about the whole coordinate. I just need to find the part, you know, like the part in that particular coordinate. Peyton?
So for number 10, I can get like the graph and everything, but I'm having trouble like remembering how to find like what am I looking at for the unit circle? Like find each other.
So you know at this point that this is in quadrant 1, right? We're looking in quadrant 1. Now you said I'm skipping all those steps because you said you were good with that part, right? Okay. So cotangent is x over y. So I'm going to be looking for the place in quadrant 1 where the x coordinate has a root 3 in it and the y coordinate has a 1 in it.
Oh, okay.
So I go to my unit circle. X coordinate has a root 3, y coordinate has a 1. So I'm looking at pi over 6. Cool? So I don't even care about the whole fraction because we're dividing anyway, so it's, you know, like you're gonna lose some of that stuff anyways. So Paul?
So when it's a single number, you're always gonna look for like that and then one, the number and then
Well, depends what the trig function is. Because if it's sine or cosine, then it's just
you just look for
x and y.
Yeah.
It's not a fraction, so I don't care. It doesn't need to be over 1.
Okay.
It's only if it's
Yeah.
tan or cotangent that I have to worry about that part,
Okay.
you know?
Did you do number 8?
On the same sheet? Yeah. Peyton, did you have a follow-up on this before I do something different?
No, I could ask on this one.
Okay. So I notice here that I have secant. So I'm going to start by just thinking of this as the reciprocal of cosine. But I want that cosine theta in the numerator, so I'm just going to flip both sides. And I know that things on my unit circle have rationalized denominators. So I'm going to go ahead and do that. Okay with that? And then if I do this, pi to 2 pi is quadrants 3 and 4. If I do all silly turtles crawl, cosine is negative in quadrant 3. So I'm going to quadrant 3 and looking for where cosine is negative root 2 over 2, which is the x coordinate. So I want 5 pi over 4. Peyton, was that okay?
So, why is like pi on the left side? Does it just not matter?
Well, when we're counting around the unit circle, when thetas are positive, we're going counterclockwise. So we're going this direction. So I just stopped writing all the intermediate things because it was just, it gets
Okay, and then
to be a lot of stuff, but
like, do you just know that to count by half a pi each quarter?
well, how many degrees is a quadrant? 90, right? They have to be. They're perpendicular, the x and y axes. And 90 degrees is just pi over 2 radians.
Okay.
So that's all I'm doing is just counting by 90 degrees to the quadrants. Does that feel okay?
Yeah.
Which is the same thing as pi over 2, right? So half a pi, 0, half, 1, 1.5, 2, 2.5, 3, 3.5, 4. And if you want to use decimals, go ahead and make them decimals. Like if that makes it easier than monkeying around with the
But it's
fractions.
just like always by half a pi?
Yeah. Yeah. Okay. Anybody else? Okie dokie. Today we're gonna do section 4.3 then. So one of the important applications that we can use for these trig functions is we can use them to take, like a complex movement and break it up into kind of simpler pieces. So imagine you have like point A and point B. One way to describe going from point A to point B might be just directly, right? But another way to describe it might be we're going to go directly to the right so far and then directly up so far. That would also get us to point B, right? So this is going to be the kind of the main idea of kind of these navigation type problems that we're going to talk about here. So I can take kind of a complicated movement where something is happening at an angle and break it into something that's purely horizontal and then purely vertical. That'll describe the same net motion. Everybody's okay with that idea? Okay. So again, in this section, we're going to be talking mostly about navigation problems. The crummy thing about navigation is that they describe their angles using something called a course or a bearing. And that definition is different than our standard position angle in trigonometry. So let's start by defining exactly how those work. Ugh, my pen. Come on back. There you go. So a course or bearing of an object is given as the angle of the object's line of travel measured clockwise starting at due north. So very different than kind of how we've defined our standard position angles that we've been using previously. The first order of business is going to be converting between a bearing and standard position. So let's take some bearings and convert them to standard position angles. So the first bearing that we're going to look at is given as alpha, and it's equal to 58 degrees. So to do this, I'm just going to kind of draw a picture. So I'm going to label my compass rose here, northeast, southwest. Bearing says start at due north, and they go clockwise. So starting at north, I'm going to go clockwise, 58 degrees. So that's my alpha. Actually, I'm going to just write that as 58. Everybody's okay with that idea? My standard position angle then starts on the positive x-axis, that's the east line, and goes counterclockwise. So what does that angle have to be? Grace, are you raising your hand? What does the blue one have to be? 32. Yeah. Because we know that 58 and 32 have to be complementary, right? Because they're both in the same quadrant. Everybody, or they'll make up one full quadrant. Everybody's okay with that? Okay. Let's do a couple more examples just to make sure that we have this, because this is an important skill. So let's say that our next bearing here is defined as beta. So it's 164 degrees. Again, we'll start the same way. So draw our compass rose. Starting north and going clockwise. So 90 degrees here and like 74 more degrees gets us down here. Everybody's okay there? And then my standard position angle starts at the positive x-axis and goes counterclockwise. So 90, 90, 90, and then how much more is that little sliver there? 16, very good. So my theta then is going to just be 90 plus 90 plus 90. If my pen wants to keep working, plus 16. So 286 is the standard position angle. Is everybody okay with that, Mackenzie? Standard position angles start with the positive x-axis and rotate counterclockwise. So that's what I'm doing. Is that okay? Okay. So again, we're trying to translate these bearings into the kind of angles that we've been using previously. Because everything that we've developed previously with like how we do sine, cosine, tangent, and all of that stuff is all based on a standard position angle, right? That was the first thing that we did before we developed the unit circle. So I can't do sine, cosine, tangent to a bearing and get the correct answer because a bearing isn't a standard position angle. I have to convert that bearing into standard position before I can do like sine, cosine, or tangent to it. Is everybody okay with that idea? Okay. So next one, we have gamma equals 221. So let's see, we have 90, 180, and then 41 more. That'll get us to 221. And then my standard position, I go 90, 90, and then how much more? 49 more. So theta is 90 plus 90 plus 49, which is 229. Is everybody feeling okay on this? Again, this is a very important skill. If you can't do this, you're not going to get any correct answers for any of the problems in this section. So just to be clear, like you need to be able to do this to answer any of the questions in this section. If you do not do this, everything is going to be wrong. Just to be clear. It's not good, but this is a relatively easy skill too. And the first step for all of our problems is just going to be simply converting bearings into standard position angles. All right, last example here. Okay, there we go. So I have delta is equal to 299. My pen is being a poopy pants. There we go. Okay. Let's draw that bearing. Starting from north, 90, 180, 270. So 29 more. And then my standard position angle, 90. And then how much more is that got to be? 61. So my theta is 90 plus 61, or 151 degrees. Do we feel okay here?
Yeah.
Yes. Good. Again, this should be relatively easy to do, but it's really a critical sub-skill for the kind of problem that we're going to look at here next. So all of your homework problems in this section are going to be some kind of like navigation problem or some kind of motion kind of problem where things are moving. So here it says a boat leaves a port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So if we kind of think about this, so we have like, we go here, this is the port, and then from here we go and we do like this, and we're asking for like that spot, right? This is like leg 1 of the trip, that's like leg 2, and we're asking for like, if it's just a straight shot, what did we do? Does that kind of make sense to you guys? Now, we drew this triangle. What's the problem here with the triangle that we've drawn? It's not a right triangle. You know what I mean? So we can't really do anything with it using sine, cosine, and tangent as we've described them. So this is what we're going to do instead, is I'm going to think about leg 1 as its own separate piece. So I have 215 degrees as my bearing. So 90, 90, and then, or 180, that goes 90, 180, and then 35 more. And I'm going to turn that into a standard position angle. So 90, 90, and then 55. So that is going to be 180 plus 55 is 235. Is everybody okay with that? Yeah. Okay. Now what I'm going to do here is, I know that we're on this for 2 hours and we're going 40 nautical miles per hour. So like my length here is going to be 80 nautical miles. Everybody cool with that? And now, just like we described here at the very beginning, I'm going to think about this as a horizontal component and then a vertical component. Everybody okay with that idea? So the horizontal component I'm going to call x1, and the vertical component I'm going to call y1. I know, I'm trying to erase it right now, but my pen is being unresponsive. So I know the length of this side is 80. And I know that this standard position angle is 235. So this side is going to, the horizontal side is going to be represented by cosine, because that's like the adjacent. So it's just going to be 80 times cosine of 235. And I want to use the standard position angle here because I want the x's and y's to be potentially negative. Because what I'm going to do is I'm going to just take the horizontal components and add them together from both legs, the vertical components and add them together from both legs. And that'll kind of get me my result, right? So what we're doing is kind of doing something like this, and what we're going to do is just kind of think about it as that. Same idea here for the vertical component, except for the vertical components we're going to be using sine. Paul?
Could you do it where you go all the way down, but the right arrow keeps going down and going to the right?
I'm not sure what you're talking about.
So like right here, could you go like down there and to the right?
Well, I mean, you could think about it doing this instead.
Okay. Does it matter which way you do it at all?
Well, you're starting at P, and you're ending at that point in the lower right.
Okay.
So, no. Mackenzie? Well, the problem says the boat's going 40 knots for 2 hours. So 40 nautical miles per hour for 2 hours is 80 total miles. Because the question's asking how far the distance. It's not actually asking like what the speed is or something. It's asking for how far it is, the distance. So in the first leg, we went 80 miles. On the second leg, how far are we going to be going? So I draw leg 2. Yeah. 165, you said? Yeah. And then, just like before, I'm going to break this into a horizontal component and a vertical component. So that horizontal component is going to be 165 times cosine 249. And the vertical is going to be 165 sine 249. The horizontal component's always going to be using cosine. The vertical component's always going to be using sine. Yes. Of course. 249. Oh, should be 89, right? Thank you. What's up? Oh, it's 162. I wrote down, yeah. Thank you. Let me go fix that. Yes. Great. Is everybody okay with that idea? Okay. So this final position then is just going to be the sum of the horizontal parts of our trip plus the sum of the vertical parts of our trip. That's going to be the new point at that final position, right? Does that make sense to everybody? And that's going to be calculator time. So notice, what mode should my calculator be in? Degrees, because the angles are measured in degrees. So I need to make sure I change that since I was using radians previous. So I'm going to do 80 cosine 235 plus 165 cosine 288. And that's going to give me 510 for my x coordinate. And then we'll do sine 235. Oops. 80 sine 235 plus 165 sine 288. And it gives me negative 222.46. So there's my port. There's my final position. So we're really talking about that as my trip, right? So how do I find the length of that line PF? This is a geometry question. We have a tool specifically to do something like this. The distance formula. Great. So the P is just 0, 0. F is x1 plus y1. I'm sorry, x1 plus x2, y1 plus y2. But really, if the other one is 0, 0, what does that distance boil down to? It's just kind of like the Pythagorean theorem, right? It's really 510 minus 0 squared plus negative 222.46 minus 0 squared. But the minus zeros don't really matter, right? Will this always be the case? Yeah. Yeah. Why would you fix your starting location at anything other than the origin? Right? We're always going to choose the starting location to be the origin. You guys know what I mean? Okay. So we'll go ahead and do that. Now, while I'm doing this, I got to be careful because that y coordinate is negative. I need to make sure I put a parenthesis around it before I squared it, because the calculator's dumb. It'll square first and then make it negative, because that's the order of operations. So that should come out to be 22.5 or 222.51. Which should make sense looking at the picture, right? You're almost going straight down. So it's almost just the y coordinate is the distance away. You have a little bit of contribution from the x, but not a whole lot because the x is real small relative to the y. Everybody's okay with that idea? The next thing that I want to do is I want to calculate its bearing. That was the other piece that the question asked for. So I want this value, right? Oh, what did it ask? I'm sorry. Was it asking for a trig angle or its bearing? Okay, I wanted the bearing. Everybody's okay with that? So that piece of it's 90. What's that piece going to be? That's like our alpha from before, right? It's made up by the x-axis and the terminal side. Everybody agree with that? So in this case, my bearing is going to be 90 plus alpha. Everybody agree with that? The question is, how do I calculate alpha? Okay, but which trig function am I going to use? If I have x's and y's,
It would be.
let me use tangent, right? Which is y over x. Will I do that every single time?
No.
You betcha. Because I'm always going to have,
You're always going to have an x and y. Okay.
yeah, because I'm always going to have the final position, which is an x and a y. So I'm going to do tan inverse, and this time I am going to use the absolute value in my calculator, only because I'm just going to steal the numbers here. So this is my y divided by my x. Since I couldn't do the absolute value part in my head because I was taking the whole number from the calculator. And that gives me 88.68 for alpha. Well, it's y, so it's the negative 222 over the 0.5, yeah. And then if I add 90 to that, then my bearing is 178.7. So there's our distance and our bearing, right? That's what we were being asked for. So we're done. Let's do another example. Well, I drew a lot of stuff because I wanted to make sure we're explaining kind of what we're doing and why we're doing things. this time we'll kind of condense things down a little bit.
Okay.
But these are long problems. There's a lot to do. So here it says a plane can travel 525 miles per hour under its own power. If a pilot flies the plane or flies at the plane's maximum speed on a bearing of 125 degrees, and there's a 35 mile per hour wind traveling at a 200 degree bearing, what is the plane's actual speed and bearing? So again, all I'm reading here is that I have two things that are interacting with each other in an additive fashion, right? Whatever that speed is doing, or whatever the wind is doing, it's like interacting with the plane's speed directly, right? Just additively. Now that may cause a net reduction in speed if they're like head on, or it might make it net faster if there like is a tailwind or whatever, but the angle is going to take care of the adding or subtracting, or whether it's a positive or negative change in the plane's speed will be taken care of by the angles. I don't have to worry about that myself. Is everybody okay with that idea? So I'm just going to think about this in the same way I did the previous version. I'm going to think of it as two separate legs. We'll break those down into horizontal and vertical parts. Add the horizontal parts, add the vertical parts. Calculate the new length, which in this case is going to represent the speed, and the new bearing. Is everybody okay with that idea? So it's going to be virtually the same idea as the previous problem. Okay? So my first leg here. So the bearing is at 125 degrees. So we have 90 and then 35 more. So my standard position angle, 90, 90, 90 plus 55. So that's going to be 305. The speed here is 525. So the horizontal component of my speed is going to be 525 cosine 305. And the vertical component of my speed is going to be 525 sine 305. So far, so good? So in leg 2, we have a 200 degree bearing. So 90, 90, 20 more. Not 300, I almost did 300 there. So my standard position is 90, 90, and then 70. So that's 180 plus 70, so 250. And the speed there is still 35. Now, just a quick look at the picture. Is this wind going to be speeding the plane up or slowing it down? Look at where the two speeds are pointing. I think it's probably going to end up slowing it down a little bit. It's hard to tell, but it looks like one of them is going to the right, the other's going to the left. You'd think that there'd be some kind of tug on that to maybe slow it down, but they're both pointing down, so it might not be slowing it down a whole lot. So my x2 is going to be 35 cosine 250, and my y2 is going to be 35 sine 250. And then my final is just going to be x1 plus x2, y1 plus y2. And it's calculator time for that. So 525 cosine 305 plus 35 cosine 250. That gives me 289.16. And then the same thing except with sines. So negative 462.94. Everybody's okay with that? So my final speed is just going to be like the Pythagorean theorem. So that comes out to be 545.8. So we did end up picking up a little bit of speed, which I guess makes sense because most of the direction is vertical, where they're both mostly pointing down. Everybody's okay so far? And then to do my bearing, so I'm plotting the point 289 comma negative 462. So we're down here somewhere. So this is my bearing. So I have 90, and then this piece is alpha. So 90 plus alpha, right? Where my alpha is always tan inverse absolute value y over x. And calculator time. So 148 is my bearing there. Yeah. I guess I had a decimal on that. Oh, 0.0. Went a little bit faster that time now that we kind of knew what we were doing, right?
Wait, why was it tan inverse?
Always.
Oh. X and Y's.
Because you have X and Y's. Okay. You want to do one more? Let's just kind of talk about the setup for this last one. That's a little bit different. We won't go through do the whole thing, but there's something a little bit different about this last one that's worth talking about. So we won't finish this all the way out. But let's talk about what's different about this one than the previous two. So a plane can travel 480 miles per hour under its own power. The pilot sets a bearing of 320 degrees. As the plane travels, the pilot notes the plane is actually traveling 325 degree bearing at 472. What is the bearing and direction of the wind? So here's what's going on. We have like the plane initially plus the wind is going to give us the plane's final stats, right? The wind is going to interact with it that way. Because we're looking for the wind, we're really going to be taking the plane's final stats and subtracting the plane's initial stats. Is that okay with that? So my P final is the bearing 325 with the speed 472. And the plane's initial was the bearing 320 and the speed 480. And that's kind of the setup. And then it really goes the same as the previous one, but we have to remember to get our wind here, we're going to be subtracting the horizontal components and the vertical components rather than adding them. But that's the big takeaway. That's the difference. In the interest of time, I'm going to just stop at this point and not finish this one all the way out because we did the important difference piece to this. Because from here, it's really the same, except you have to do that subtracting of the components instead of adding. Otherwise, everything else goes exactly the same. Is that okay with you guys? Okay.